Ever flipped a switch in your home and watched the lights come to life almost instantly? It feels like magic, but it's actually a fascinating science at work. That's electricity in action, powering up your space in the blink of an eye. Electricity is energy on the move, and the name for this movement is electric current. It's what makes all our electronic devices work, from the smallest gadget to the largest appliance. Imagine a river, but instead of water, it's made up of countless tiny, charged particles called electrons, all flowing together along a path. When you turn on a lamp, you're actually completing a circuit. This allows electrons to travel from the outlet, through the bulb, and back again, lighting up the room. But if the circuit is broken, like when you flip the switch off, the flow of electrons stops and the light goes out. The path must be complete for current to flow. The amount of electric charge passing a single point each second is called the current. The more electrons that flow, the higher the current, just like a river with more water flowing faster. Small devices, like your phone or a tiny LED, use only tiny currents, while big appliances, such as refrigerators or air conditioners, need much larger currents to operate. The materials we use to build these paths are important. Some materials let electrons flow easily, while others block their movement almost completely. Materials that allow this easy flow of electrons are called conductors. Metals like copper and aluminum are excellent conductors, which is why they're used in wires. On the other hand, materials that block the flow are called insulators. Rubber, glass, and plastic are common insulators, keeping us safe from electric shocks. Knowing which materials conduct and which insulate is crucial for using electricity safely and efficiently in our daily lives. Think of conductors as superhighways for electrons, letting them speed along, while insulators act like dams, stopping the flow in its tracks. This basic difference between conductors and insulators shapes how we use electricity every day, from lighting our homes to powering the world around us. What makes a material a good path for electric current? The answer lies in conductors, materials that allow electricity to flow with ease. Conductors let electric charge, usually electrons, move freely from atom to atom, creating a smooth and efficient flow of current. Metals like copper and aluminum are top conductors, which is why they're used in wires and electrical circuits everywhere, from your home to massive power grids. Their secret is the abundance of free electrons that aren't tightly held by atoms, forming a sea of mobile charge that can move in response to an electric field. When a battery is connected, these electrons drift in one direction, creating a steady electric current that powers devices and lights up our world. Copper wires in your walls, aluminum in power lines, even salt water and the human body can conduct electricity, though not all as efficiently as metals. The key to being a good conductor is having lots of mobile charge carriers, particles that can move freely and carry electric charge. Not just metals, some liquids, like salt water, and even gases under certain conditions, can conduct electricity by allowing charged particles to move. If a material has free-moving charges, whether electrons or ions, it's considered a conductor. That's what makes the flow of electricity possible, powering everything from tiny gadgets to entire cities. Conductors work because their free electrons are always moving randomly. When an electric field is applied, these electrons drift together, forming a current. The electric field's push is nearly instant. Flip a switch, and electrons everywhere in the wire start moving. Think of a tube of marbles. Push one in, one pops out the other end. Conductors have low resistivity, little friction for electrons, so current flows easily and little energy is lost as heat. High conductivity and low resistivity are two sides of the same coin. Metals are perfect for wiring because they have many free electrons and low resistance. That's why they're the backbone of our electrical systems. The structure of conductors makes them ideal for carrying current. Now, what if we want to stop electricity? We use insulators. Insulators resist the flow of electric charge. Think of them as brick walls for electrons. The plastic or rubber coating on wires is an insulator, keeping electricity safely inside. In insulators, electrons are tightly bound to their atoms. No free electrons, no current. Common insulators: plastic, rubber, glass, dry wood, and even pure water. Insulators keep us safe by blocking unwanted current flow. When an electric field is applied, electrons in insulators can't break free. No mobile charges means no current. Without insulators, handling electricity would be dangerous. Insulators block current because their electrons are locked in place. Their atomic structure creates huge resistance, like pushing a car through mud. Even strong electric fields can't free their electrons. Insulators have extremely high resistivity, so almost no current flows. When voltage is applied, electrons can't jump from atom to atom. Only with a massive voltage, like lightning, can an insulator break down and conduct. This is called dielectric breakdown, and it's rare in daily life. Insulators have low conductivity and high resistance. They're essential for safety, but no insulator is perfect. Their main job: keep electricity where it belongs. Let's take a closer look and compare conductors and insulators side by side, exploring what truly sets them apart at both the atomic and practical levels. Conductors are materials packed with many free electrons. These electrons can move easily, which gives conductors their low resistivity and high conductivity. The energy gap between their valence and conduction bands is very small, making it simple for electrons to jump and carry current. Insulators, on the other hand, have tightly bound electrons that are not free to move. Their resistivity is high, conductivity is low, and the energy gap is large, so electrons can't easily jump across and conduct electricity. When an electric field is applied, conductors respond by letting electrons flow freely, creating an electric current. Insulators, however, keep their electrons locked in place, so current can't flow. Some common examples of conductors include copper, aluminum, and even salt water. These materials are chosen for their ability to let electricity pass through with ease. In contrast, rubber, glass, and air are classic insulators. They're used specifically to block or contain electricity, keeping us safe from electric shocks. Conductors are essential for making wires and pathways that allow electric current to travel efficiently from one place to another. Insulators, meanwhile, provide safety and isolation. For example, the plastic or rubber coating around wires prevents accidental shocks and keeps circuits working properly. The key difference between these two types of materials is the freedom of their electrons, how easily they can move or how tightly they're held. You can think of conductors as a lively dance floor where everyone is free to move and interact, passing energy from one to another. Insulators, in contrast, are like a formal dinner party where everyone stays in their seat. No one gets up or moves around, so energy stays put. This atomic-level difference is what shapes all their properties, from how they handle electricity to how they're used in real-world applications. That's why metal spoons conduct heat and electricity, while wooden ones don't. Understanding this helps explain so many everyday phenomena. These aren't just textbook ideas. They have a real impact on our daily lives, from the appliances we use to the safety features in our homes. The partnership between conductors and insulators is essential for technology, making our modern world possible by balancing the flow and control of electricity. In real life, conductors and insulators work together. Power cords use copper wires, conductors inside, coated with plastic, insulators outside. The conductor carries current. The insulator keeps it safe and contained. Without insulation, touching a wire could be deadly, and wires could short circuit. High-voltage power lines use aluminum cables, conductors, suspended by glass or ceramic discs, insulators. The insulators prevent electricity from leaking into the towers or the ground. This teamwork is everywhere, from phone chargers to power grids. Conductors do the work. Insulators provide the safety. Both are vital for safe, reliable electricity. Not all materials are just conductors or insulators. Some are semiconductors. Semiconductors, like silicon, have conductivity between that of conductors and insulators. Their conductivity can be changed by adding energy or impurities, a process called doping. Doping creates N-type, extra electrons, or P-type, extra holes, semiconductors. By combining N-type and P-type, we make diodes and transistors. Diodes let current flow one way. Transistors act as switches or amplifiers. Semiconductors are the foundation of all modern electronics. Their ability to switch between insulating and conducting is what powers computers and smartphones. They're the bridge between conductors and insulators. This unique property drives the digital world. Let's see the difference between a conductor and an insulator with numbers. Take two wires, same size, one copper, one glass. Copper's resistance is tiny, about 0.007 ohms. Glass's is astronomical, about 10 watts, 18 ohms. Connect both to a 12-volt battery. Copper lets a huge current flow. Glass, almost none. The copper wire would melt from the current. The glass rod barely lets a single electron through. This shows how conductors are open doors for electricity, while insulators are fortress walls. The difference isn't just big, it's billions of times bigger. That's why we use copper for wires and glass for insulation. The numbers make the difference crystal clear. Conductors and insulators are worlds apart in how they handle electricity. We've seen how materials fall into three categories: conductors, insulators, and semiconductors. Conductors like copper let electrons flow freely, powering our world. Insulators like rubber block current and keep us safe. Semiconductors like silicon can switch between conducting and insulating, enabling modern electronics. The difference comes down to how tightly electrons are held. Conductors provide the path, insulators provide the safety, semiconductors provide the control. From light switches to smartphones, these principles shape our lives. Together they form the foundation of our technological world.